All right, this is part 5 of estimating existing sprinkler design, and we'll put together the matrix and the pressure losses to provide water to the design area. Now, my intent right from the start of this thing was to videotape me sketching out a system, and unfortunately, I don't have access to a pipe schedule system, and I definitely don't have access to any risers. So that's a problem. I haven't really sorted out how to get around that yet for a tree system anyways. I should be able to do it for a grid system. I've already gone out to a big box at Home Depot and sketched out a grid system. And that's pretty straightforward, but there's still some quirks in getting the numbers. Now, the reason that I want to sketch out the system is that essentially what I'm doing is spoon feeding the information to you, and it's pretty easy in this form. What really makes it challenging is looking up at piping that's 25 feet off the floor. Maybe it's dark up there. I've got a client that's breathing down your neck and wants you to move on. There's forklifts that are maybe zipping around, and it's a daunting task to really grab information quickly, and you really need to know what you're doing. So I'm disappointed that I don't have that system. I'm disappointed I kind of I can't create that scenario where you're kind of on the run to grab as much information as you can. But let's just go through this, and I do promise at some point once I find a tree system that I'll estimate. I'll do a video and just add it to this as part 5B. So let's move on to slide 2. As I've said in all the previous videos, this is for entertainment purposes only. Because we've cut so many corners and used estimates, you really can't make any final decisions or make changes to a system without doing a full set of calculations. This is really for estimate purposes only. In this particular example, we will be looking at a 125 pipe schedule system. It's called extra hazard pipe schedule system. This table A 2854 is from the annex of NFPA 13 2022 edition. And as we said, it's one sprinkler being fed by an inch, 2 by inch and a quarter, and 5 sprinklers are being fed by inch and a half pipe. If you recall, we looked at AXA XL table 1 on page 5 of an 8-page document. This covers the extra hazard pipe schedule layout, and it was for head line spacing, had certain densities, which we'll cover later, and depending on the piping configuration, it provided a water requirement and a pressure requirement as well. We have disregarded the pressure loss through fittings, although I did introduce the idea of equivalent length. I do want to mention that double check valves will be installed in sprinkler systems. There'll be shutoff valves on either side of the double checks, and those double checks will have a friction loss associated with them. There'll be additional piping, in some cases, as these double checks may needed to have been fitted into existing systems. But for right now, what we'll do is just determine what the friction loss is, the pressure loss is through the double check valve. And the way we determine the pressure loss through the double check valve is a series of graphs that'll be part of a cut sheet. In our particular case, we will be looking at a 6-inch double check valve, and you can see it along the x-axis. There's GPM, and the y-axis will be PSI. So, for instance, at a flow of 1,000 GPM. It looks like it's somewhere in the vicinity of between 4 and 5 psi pressure loss. Let's just go through an example. We have a 125 wet sprinkler system. All the piping is schedule 40. Again, remember that comes into play when we're looking at friction loss through pipe during flow. It's a center fed 8 head per branch line system with 10 feet between lines and 9 feet between heads. The heads are 1/2 inch K.56 sprinklers. We have, as part of the cross main, right outside the 3000 design area, we have 20 feet of 4-inch line, and we have 150 feet of 6-inch line. And that's also all schedule 40. Then we have a 6-inch double check as noted back on slide 5. We have a 22-foot elevation from the floor to the sprinklers. And let's see if we can calculate the overall demand in GPM and pressure at the base of the riser for a system protecting a woodworking shop. So let's just take a look at this 125 branch layout. And it, as it states, one head is being supplied by the 1-inch line. 2 heads are being supplied by the 1 1/4, 1.25. 5 heads are being supplied by the 1.5 inch. That's all the 125 system says. I do want to comment just a bit on how we're establishing the adequacy of these sprinkler systems. When they were designed back in the day, they were designed back in the concept of having a layout according to the scheduling, and then a water supply that would had a pressure at the base and a flow and duration, depending on and the duration really depended on whether you were tied to a central station or not. It's been for a long time, the extra hazard systems have not been allowed to be anything other than hydraulically calculated. But when we're doing our analysis, we're not basing the acceptability of the system on the piping layout and the water supply alone. We're basing it on the density that it's capable of providing, which is not how it was originally designed. So just keep that in mind when you are going through this exercise. If you recall, we determined that a woodworking operation was a EH1, extra hazard 1 occupancy, and would require a density of 0.28 GPM per square foot over 3,000 square feet. More to follow on that in upcoming presentations. So with our example above of 10-foot line spacing, 9-foot head spacing, 0.28 GPM per square foot density, we require within that 3,000 foot design area a water supply of 1101 at 54 psi. But we still need to get the water from the street through the piping to that 3,000 square foot design area. And as we indicated, we had 20 feet of 4-inch line. So we're flowing 1100 GPM into that 3,000 square foot design area. So the 4-inch Schedule 40 pipe has an ID of 4.026. And again, it's important to know the schedule of the pipe in order to come up with closer friction loss numbers. And then I have a table, I have a number of tables to determine the friction loss for various type pipe. In this case, I went to one of the tables and it told me for 1100 GPM with a C of 120 because it's all wet system and C is 120 for NFPA 13 wet pipe systems. Per foot loss is 0.309. So I multiply the 20 feet times the 0.309, come up with 6.2 psi friction loss through the 4-inch. Now we could have calculated it otherwise. Could have taken the friction loss the following way. We had 1100 GPM flowing through a C of 100 pipe, which provided a per loss foot of 0.432. And if you recall there, and that per loss foot times 20 would be 8.64. And if you recall, there was a conversion table to convert losses from 100 to, I think it was 150 to 40, I think. And so we would find the conversion for C120, which is 0.714, and multiplying the 8.64 times 0.714, we arrive at a number of 6.2. And so it's just to show you that there's a couple of ways of going about getting that friction loss through pipe. And just to show there's additional methods to determining pressure loss, we also went online and used one of the online calculators for 1101 GPM through a 6-inch line. Again, called it Schedule 40, so I put the 6.065 internal ID, the ID for that Schedule 40 pipe. Input at 1100, C of 120, 150 feet of pipe, and came up with a total friction loss of 6.3. So let's start to add up all the pressure losses. As you recall, there'll be an elevation loss for getting the water from the floor to the sprinkler. And we said that was 22 a foot elevation times 0.433, resulting in a 9.5 PSI elevation pressure loss. We looked at go back and look at slide 5 when you get a chance, and you'll see that the friction loss, the pressure loss through the double check when flowing 1100 is about 5 PSI. And then of course in the previous 2 slides, we calculated that the 4-inch pipe of 20 feet had a 6.2 PSI loss, and the friction loss through the 100 feet of 6-inch line had a pressure loss of 6.3. We add up all those losses, excluding fittings and alarm check valve, we get about 27 PSI. The alarm check valve is generally good for 2 or 3 PSI. I'm just ignoring it here. The fittings would result in some loss as well. So excluding that, just not to complicate matters, we've lost about 27, but probably closer to 30 PSI. So if you recall from the table, to get the 0.28 GPM over 3,000 square feet to meet the occupancy of a woodworking shop, we needed 1101 GPM at 54 PSI, but that's only within that 3,000 square foot design area. We also need to add in the 27 PSI of additional losses to get the water from the street to that 3,000 foot design area. That results in 81 PSI. So at the base of the riser, where essentially where the sprinkler pipe comes through the floor into the building, we require 1101 GPM at 81 PSI. Now let's just say, for the point of discussion, that we determine that we have 1101 GPM at 90 PSI. Would that be sufficient? And if you think about it for a second, obviously, if you have 90 PSI and you only need 81 PSI, then of course it is sufficient. But we'll cover that in more detail later. What are the conclusions that we can come up with based on our review of these pipe schedule systems? I think we can say with some level of confidence that the 1, 2, 3 systems in place from 1905 to 1940 and the 235s in place from 40 onward are likely adequate for ordinary hazard occupancies, given a decent water supply. And we're going to discuss water supplies in the next presentation. And they can deliver extra hazard 1 water supplies with a very strong water supply, and we proved that in the last video. The 125s are adequate for obviously the OH1, the OH2s, the kind of low to moderate fire loaded facilities, and the EH1s. Although, as we saw in that last example, that's an extra hazard 1 occupancy, that woodworking shop, you needed 1100 GPM at 80 PSI. There's not an insignificant amount of water. There's a fair amount of water to provide that type of pressure and water supply. So be cognizant that pipe schedule alone doesn't do the trick. You still need a fair amount of water to start to meet some of those more moderately loaded or what they would call higher combustible loaded occupancies. And then, of course, the EH2s really are a challenge for almost any piping system to meet. I hesitated to include this slide, but I will include this slide. And I call it unicorns, and that's because it's unlikely, although this slide from FM datasheet 2-77 does indicate that it is possible to obtain really significant sprinkler designs of 0.5 and 0.6, which are much higher than the 0.28 that we were talking about with ordinary hazard pipe schedule system, with center fed pipe schedule systems. And that be based on the head spacing for the most part. I'll be honest with you, I've done a lot of, I've looked at a lot of facilities and installations, and I don't know that I've ever seen a pipe schedule system that's capable of putting out that kind of water flow. It's possible. I mean, they say it's possible. So I just throw that out there. If you see something that's really has unusually tight array of sprinkler layout, then that's when you really want to take the sketch and run some calcs and see where you stand. The next video will be on estimating water supplies. Now, in some cases, you're going to be able to call the water department and they will provide you with water tests within the area. A lot of cases they won't, or a lot of cases they won't get back to you. It's a very interesting situation calling up a municipality. So you're confronted with having all this piping and all these numbers to support what the sprinkler system demand is, but without having a water supply, none of that information is of any relevancy. You've got to know that you have the water in the street to support the demand. So what we're going to do is discuss how we can estimate water supplies. A really interesting discussion, and some techniques to go about coming up with some numbers that are relatively valid. I mean, they're no substitute for actual flow test. Now, before you watch this video, I suggest that you go online and watch any number of videos that will outline how to do a hydrant test and how to determine a water supply based on flow of hydrants. I went on and did just a quick search today, and there's countless videos on the subject. There's no sense in me rehashing old territory. As a matter of fact, we used to teach a course at our fire lab, and it was an 8-hour course on water supplies, tanks, etc. So it's a subject that can be very lengthy, but it's also a subject that can be covered quickly. So my suggestion is to go online, watch some of the videos, be able to at least understand what static and residual means with regard to a water supply, and then come back and watch the next video, which will be video 6, outlining how to estimate water supplies. Any questions, by all means, drop them below. Thank you.